morning children, welcome back to your chemistry class. So today in the States of Matter chapter, we are going to talk about Graham's law of diffusion and effusion. So before I begin to explain you Graham's law, first let us understand these two words first. So what do we mean by this word diffusion? Diffusion is what? It is the property by virtue of which a gas, it can spread and occupy the entire available space. That is called as diffusion, right? Why this happens? Because the diffusion takes place when one gas intermingles with the other gas, then it is termed as diffusion, correct? So I write down the definition over here, that the property by virtue of which a gas spreads and occupies the entire space is called diffusion. So let's talk about some examples of diffusion. Like the fragrance of the perfume, it is what? Due to the intermingling and the movement of the particles or the molecules of the perfume into the air, correct? Then even the foul smell of that rotten egg H2S gas that you must have smelled number of times, that is also due to the diffusion of molecules into the air. Then even the pleasant odor of the food which mummy cooks, you all can easily smell, which comes from the kitchen, that is also due to the diffusion of molecules through the air, right? So I hope this word of diffusion is clear to you. Now we come to the new word, that is effusion. What is effusion? Effusion is the process by which the gas under high pressure, it escapes in fact through a very small hole, right, in its container into another available space. Then that is called as effusion. So I write it down and then I'll give you some examples over here also. Like effusion is the process by which a gas under high pressure escapes, right, through a small hole in its container into another available space, right? As the gas it escapes out, it diffuses and it occupies another space. So let's talk about some examples of effusion also. Like for example, the air that escapes through a hole in a punctured tire, you hardly come to know and your tire gets punctured. So that is because of the very minute hole that is present in the tire. That is effusion. Okay. Then another example is escaping of your perfume vapors through the small hole in the atomizer of the bottle. That is another example of effusion. Even if you blow a balloon and keep it overnight, and if it has a small hole, then in the morning you will see that the whole air has escaped and your balloon has become too small. So that is another example of your effusion. I hope this is very clear. So now in 1831, Thomas Graham, he proposed a law to report the rate of diffusion or effusion of the gases. So he had observed that lighter gases, they diffuse faster than heavier gases. What did I say? That what did he deduce? Graham He deduced that lighter gases, they diffuse faster than the heavier gases, right? So this observation was supported by the fact that the speed of the molecules of the gas, it completely depends upon the temperature and the molecular mass, right? So some of the important points now we are going to discuss about Graham's law of effusion. So the first point about Graham's law of effusion is what? That at constant temperature and pressure, the rate of effusion of a gas, it is always inversely proportional to the square root of the molar mass of the gas. I repeat, what did I say? That at constant temperature and pressure, right? The rate of effusion, this is called as rate of effusion. It is inversely proportional to, what did I say? The square root of the molar mass of the gas. So that means 1 upon molar mass, and this becomes what? I can write it down like this, or I can write it down is equal to 1 upon under root m. This is what did I say? This is what I said. I repeat, what did I say? At constant temperature and pressure, the rate of effusion of the gas, it is inversely proportional to the square root of the molar mass. Square root of the molar mass, it can be written like this, or it can also be written like this. Clear? I hope this first point is very clear. Now let's talk about the second point. It says that the relative rate of effusion of two gases, namely say A and B, under similar conditions of temperature and pressure, how can they be then written? So RA upon RB. What is this? The relative rate of effusion of gas A and gas B, right? They will be equal to what? mB upon molecular mass of A, right? This can also be written as, or RA upon RB is equal to under root mB upon MA. Clear? I hope the second point is also very clear to you. Then we come to the third point. Since the density, it is always directly proportional to the molecular mass, then in that case, what can we write? RA upon RB. This can be equal to what? What had I written over here? MB upon MA, right? So this will be equal to dB upon, for gas B, density of gas B upon density of gas A, 1 by 2. Or this can also be written as under root D2 upon D1. I hope all these 3 points about Graham's law of effusion is clear to you. Now, with respect to time of diffusion and rate of effusion, let us understand. I said time of diffusion and rate of effusion, right? So let us suppose that at constant temperature and pressure, right, a volume V of a gas, gas A, it effuses in time TA. What did I say? I said volume of gas A effuses in time what? TA, right? Then the volume of the gas that effuses in unit time will be equal to what? It will be equal to volume of gas that effuses in unit time will be equal to V upon Ta, right? Therefore, rate of effusion of gas A will be equal to what? Ra will be equal to volume effusing upon time taken. So what is volume effusing? That is V upon what is time taking? That is Ta by the gas A. Clear? At volume, gas A effuses in time Ta. This is what I wrote over here. Now, suppose that the effusion of the same volume of another gas B, right? So, at V, gas B effuses in time Tb. Then, what is the rate of effusion of gas B? This will be equal to Rb is equal to volume effusing upon time taken. So what is volume effusing? V upon Tb. Therefore, what can we say? The relative rate of effusion will be equal to Ra upon Rb, which is equal to Tb upon Ta. Clear? This is what we have to understand. What is the rate of effusion? Rate of effusion for the two different gases will be the time taken by the gas B upon time taken by gas A. Now, what are the applications of Graham's law of effusion? The separation of the isotopes of an element, it is completely based on Graham's law of effusion. So, during effusion, the lighter isotopes, they escape faster from the holes in the barrier, leaving behind the heavier ones. Even the Graham's law of effusion, it provides a method to determine the molar mass. So this will be one of the numerical that I am going to tell you. Now let us understand certain numericals that are based on Graham's law of diffusion or effusion. The first question. Let us understand which one will diffuse more rapidly, helium or oxygen? Which one? At 300 Kelvin. So let us understand which of these two gases, helium or oxygen, will diffuse at 300 Kelvin. So your rate of diffusion for helium upon rate of diffusion for your oxygen will be equal to what? The molecular mass of oxygen gas upon the molecular mass of helium gas, square root, if you remember, right? So this will be equal to what? This oxygen will be 32 upon helium is what? 4, 1 by 2. So this will be equal to 2 under root 2. Therefore, we can say that rate of diffusion of helium is equal to 2 under root 2 the rate of diffusion of oxygen, which will be equal to approximately 2.8 to 8 R of oxygen. Okay, so over here, what did we study? That helium will diffuse 2.82 times faster than oxygen at the temperature that is given 300 Kelvin. Clear? I hope this first question is clear to you. Let's move to the next one. Let's talk about second numerical. Let's say small amount of ammonia and HCl are released simultaneously at the opposite ends of a 2-meter long tube. At what point the formation of ammonium chloride would start? Okay, and let me give you the molar mass of HCl. It is what? 36.5, and that of your ammonia is how much? 17. So let us look at the solution, how to understand this. So let me first make you understand this is a long tube. Okay, this is your long tube. This long tube is how many meters long? As I had just given in the question, it is 2 meters long. It says small amount of ammonia and HCl, they are released simultaneously at the opposite ends. So from here, suppose we add HCl, and from here NH3 is added, right? Then it says that at what point the formation of ammonium chloride would start. Suppose my formation somewhere starts over here. Suppose somewhere it starts over here, right? So let the distance from HCl, where this formation of NH4Cl is formed, be x, right? Then from ammonia side, when it will be formed, it will be formed at 2 minus x. This will be the distance. Clear? Is this point clear to all of you? Now let's look at the rate of diffusion of HCl. This is our HCl will be equal to what? Distance moved by time taken. Okay, so distance is how much? X upon time taken. Time taken is how much? T. Then rate of diffusion of ammonia. This will be how much? NH3 again. Distance moved upon time taken. Distance moved is how much? 2 minus x upon time taken is t. So R HCl upon R NH3 will be equal to x upon 2 minus x. Now this is equal to what? Molecular mass of NH3 upon molecular mass of HCl whole into half. Okay, so this is equal to what? X upon 2 minus x. So what is the molecular mass of ammonia that was given to you? I'll do it over here. 17 upon 36.5. This is equal to x upon 2 minus x. Can we solve this? If you solve this over here, solve for x. X means from HCl the distance where the formation of NH3 will be this, and minus that x from 2, you get the distance from ammonia. Is that clear? So the formation of NH4Cl would start when HCl has moved your x distance, that you will calculate from here, and when the distance moved from ammonia will be from that x you subtract from 2, you get the distance of the formation of ammonium chloride from ammonia, right, inside the tube. I hope this question is clear to you, all of you. Now another question. Let's take another question. It says that the rate of diffusion of methane at a given temperature is twice that of a gas. What is the molecular mass of that X gas? So what are we going to do over here? The rate of diffusion of gas, remember it is inversely proportional to the square root of the molecular mass. So let's write down the rate of diffusion of the gas CH4 methane upon that of that gas X is equal to, if I write it down like this, M, that of X upon molecular mass of CH4. Now, since rate of diffusion of methane upon rate of diffusion of that gas X is equal to 2, it says no, temperature is twice that of a gas, okay, and the molecular mass of methane is how much? 16 grams per mole. 16 grams per mole. Therefore, let's write down molecular mass of X upon 16 is equal to 2. Can we calculate molecular mass of X? You will get to as 16 if you remove this into cross multiply 4, right? So this will be equal to 16 for the 64 grams per mole, right? So with this I wind up over here. I will be sending you more numericals, solved numericals. You can go through them. Thank you.